Right, everybody, look into it. Chemical equilibrium is something where you will be learning various types of reactions. First of all, in broad way, reactions can be categorized into two kinds. One are irreversible reactions, the other one are reversible reactions. If the direction of the reaction is only in one way, that means either reactant to products you're getting, then we call it as irreversible reactions. When will you notice that? If at all there are any precipitations happening, or if there is a strong acid strong base type of reactions happening, or if the reactions are happening in open vessels, okay, in such scenarios you will call them as irreversible reactions. Okay, let me put some examples. You can see KCl plus AgNO3 is giving AgCl plus KNO3. You can see there is a precipitate forming. So whenever there is a precipitate formation, usually the reactions will go always in the forward direction. Same way, if you have a strong acid, strong base, reaction will always drive in the forward direction. The reverse is impossible. That means you can't take a common salt, add it to water, and expect it will produce HCl. That's not correct. Similarly, if at all I have calcium carbonate, slightly on decomposition, it is becoming calcium oxide plus carbon dioxide gas. But if you do not contain this carbon dioxide gas, that means the reaction will only be in the forward direction. We can contain this or we can hold this carbon dioxide as long as you make this heating in closed container. Got it? So if the same reaction was in a closed container, it is a reversible reaction. But in this case, if it is an open vessel, then it is an irreversible reaction. Got it? Now coming to the reversible reactions, if the reactions drive on both the directions, then it is called reversible. That means reactant is giving product, product is also giving reactant. In such cases, if there are reversible reactions, we will use this arrow, the half arrow forward, half arrow backward. It represents the reaction is happening in both directions. Second, these reactions can only be achieved in closed vessels. Reactions like N2 gas and 3H2 gas is converting into ammonia. The same ammonia will decompose on its own to convert back into nitrogen and hydrogen. So that's how an equilibrium is established here. Got it? Same way, PCl5 is a gas which will decompose into PCl3 and Cl2. As long as you keep it in the uh, closed container, right? So this will always have a reversible reaction form. Same logic if you have CaCO3 on heating, okay? See how the symbol is changing now. CO solid plus CO2 gas, this in closed vessel. Okay. Similarly, if you have a weak acid strong base, if you have weak acid strong base, weak acid and weak base, and strong acid and uh, weak base, any of such combinations are being observed, that means they will also exhibit equilibrium reactions. Okay, let me show you with some example here. For instance, weak acid like CH3COOH, strong base like OH minus. These two can react, convert that into CH3CO minus plus H2O. Okay. In this situation, again the CH3CO minus will take H plus and convert back into the reactant side. So such type of reactions are called as reversible reactions. So I hope all of you got a gist of what is irreversible and what is reversible type of reactions. Okay. Now we use the word chemical equilibrium clear if the forces comes to a compromise from both the directions. So there is certain force from the reactants which is trying to push towards product, And if the same type of force has been acting on the opposite direction of equal magnitude, then we say equilibrium has been achieved. And mathematically, how do we say it? We say it this way: the rate of reaction in the forward direction is equal to rate of reaction in the backward direction. Acha, how do we measure rate beta? Rate is some change with respect to time. Now here that change is change in concentration. So change in concentration per time of the reactants will be same as change in concentration per time of the products. So that means whatever the amount the product is forming, the same amount is again converting back to reactant. Okay. So you can see all reactants and products will have lowest energy possible. Okay. Once equilibrium has been achieved, once you get an equilibrium, that means we can say now all the reactants and products are at their lowest energy. And molecules of the reactants and products are at maximum entropy. Okay. Because entropy of the universe, right? If you, Acha, this is something which we have learned in thermodynamics, but in case if students are not clear with it, I'll just help you with the basic definition again. Everybody look into it. Yeah. So by definition, what is entropy? Entropy change is always equal to dq reversible by t. Just remember it like definition. What does it do? It will be measuring change in randomness. That means more the change in randomness, right? That means more is the entropy that is changed. So entropy is like measure of chaos or measure of randomness. So how do we measure it? dq reversible by t. So what is dq reversible? dq reversible means heat supplied to the system reversibly. If you are supplying any reversible type of heat, that divided by the temperature at which it is happening is ds. Now this is about ds of the system. That means rate of change of entropy, right? I mean change of entropy of the system. And reversible reactions, for reversible reactions, change of entropy of the surroundings will be equal to change of entropy of the system. And that implies total change of entropy, which is system plus surrounding, will become zero. Okay. So when equilibrium has been achieved, okay, so remember that when you equilibrium has been achieved, that means the entropy is at maximum. So the difference is zero, because if that is a maximum point where you can reach, if at all you try to figure out any difference we cannot see it, because it has already reached to a maximum amount. Clear? So therefore, or you can put it this way, the differential part at a maxima is zero, right? And entropy change at this maxima is zero. Got it? So therefore, you can notice that we are talking about the total entropy, and for total entropy, it has already reached at maximum point. Clear? And see, a chemical equilibrium is always dynamic. That means it is never stopping. So a reactant is continuously converting into product, and product is continuously converting into reactant. Yes, one thing you will see, the the equilibrium concentrations, equilibrium concentrations of reactants and products is constant. That means that is not going to change. Reactants concentration and products concentration will remain same. Okay. So notice that concentration of the reactants and product remains same at equilibrium. Okay. How do we perceive this? See, one thing, whenever we make a reaction, product is never there in the starting point, right? पहले हम लोग सिर्फ reactant लेते हैं, then the product will form. And product जितना बना है उसमें से थोड़ा product फिर reactant में आएगा. And this is a circle that it will develop over time. Agreed? So graphically, if at all I have to mention the same thing, how would I show it? See, this is the way I can represent that. This is a graphical representation. That is, in case if you have to mention how the concentration changes, and you see, one is this way, the other one is this way. Now, what does this mean? This is the concentration change of the reactant side, and this is the concentration change of the product side, how the product is changing. But now notice it, after this point onwards, they have reached constant value now. This is like a constant value. So the time where it has reached, this is with respect to time. Okay. So this is called as equilibrium time. That means the time required to reach the equilibrium. Right. After this, the product concentration and the reactant concentration remains constant. Clear? This is how the graph of graph of concentration versus time looks like.
Can you explain the graph again briefly?
Now, initially, let us take the example of nitrogen, hydrogen and ammonia. आप ऐसे समझो आपने नाइट्रोजन और हाइड्रोजन सफिशिएंट क्वांटिटी में लिया है इनिशियली और दोनों का कॉन्सेंट्रेशन समवेयर हियर इज द concentration of, let's say I'm talking only for nitrogen because that is a reactant, and ammonia which is a product. So this is a nitrogen gas concentration initially, but over a period of time what should happen, it should keep decreasing and reach to a point where it has become constant. Now after that it is not changing. Likewise, if you notice the products also, products, once you get ammonia, correct, you will hardly notice any change here. Concentration of that product remains constant. Clear beta? If that happens, see, if this happens, that means equilibrium has been achieved. Okay. Notice if you have N2 plus 3H2 giving 2 moles of NH3 at T equal to 0, that means at this is the algorithm which we will be writing always. That is initial time, there is concentration, let's say A concentration of nitrogen and A concentration of hydrogen, and there is nothing. So 0 of ammonia initially. At T equal to T, that means A minus X, and this will A minus 3X, and this will be 2X. Got it? And AT, so this represents how much moles of, you know, nitrogen is been consuming with hydrogen to produce ammonia. Okay. So now, suppose if I have to write how much is the rate of change of nitrogen, this is called as rate of disappearance of nitrogen. Okay, or I can also call it as rate of rate of change of reactant. Same way we can write it for products. See, have you noticed that suppose if this is where the nitrogen's initial concentration is, now at this point what is the concentration? It has decreased, correct? So over the time it is always decreasing. Rate is like speed. So speed of the reaction keeps decreasing specifically for nitrogen. So how do I represent this? Minus is essential to show that the speed is always a positive value. Similarly, I can write it as d of ammonia, rate of change of ammonia with respect to T, as rate of formation, rate of formation of ammonia, rate of formation of ammonia. Clear? Now you can see this is rate of reactant, rate of product. At equilibrium, what would happen? At equilibrium, the rate of reactant and the rate of product becomes equal. That's when we say the equilibrium has been achieved. So if I put the same thing graphically, how does that represent? See, it is like this. From here to here, take the other color. From here to here, you are noticing that how the rate of product is increasing. And from here to here, like this, initially, somewhere here we had, correct? So this is reactant graph and this is product graph. Okay. Now, what have we noticed here? So these two are becoming equal, correct? So at some equilibrium concentration. So this is the rate definition with respect to time. So the rate increases for products and rate decreases for reactants, and both will have the same value. At that point, the concentration of the reactant and products become constant. And this is the equilibrium, uh, the time taken for equilibrium to achieve. Okay. So please do check, everybody. If you have any doubt so far, you can stop me and ask me out. Correct. Then I'll discuss it further. I'll just take that one. Check. Okay. Find correct graphs of the following for an equilibrium. For an equilibrium. Okay. So basically, they have given different reactant, different parameters of the x-axis and y-axis, and different types of graphs has been given, and you are supposed to figure out which of them are correct ones. Starting with the first one, here one graph was given like this. Okay, and it is mentioned that this is the concentration versus time. This is the reactant concentration, and this is the product concentration. Second one, all right, it is given like this: reactant here, product here, like this. Here also it is like this. All right. Now this also given as a part of concentration versus time. This is reactant, this is product. All right. Third time, one more reaction is given like this. Now this is given, this is reactant, and this is product concentration. And this is concentration versus time again. Okay. The other one is given like this. This is reactant and product. So this is the reactant concentration. This is the product concentration, how it is changing. Concentration with respect to time. And next, the graph is going like this and like this. This is the equilibrium time. Now here it is given as rate, rate versus time. And one more graph given is like this. Again, rate versus time. And last thing is like this. This is reactant concentration, product concentration. This is rate. Okay, sorry. This one is not concentration, rate. Rate of reactant, rate of product. Now, tell me, out of these given 7 graphs, which of them are correct? Which of these are correct ones? See the first case. First case is the reactant concentration is decreasing, product concentration is increasing. That is pretty much the perfect definition, when it comes to equilibrium. Second thing, they both are reaching to a same point. Okay. So that means the reactant concentration is same, product concentration is same. But thereafter, there will not be any change. That means reactants concentration is not changing, product concentration is not changing. So that is what we expect at equilibrium. So the first graph is correct. Similarly, second graph, the reactant and product graph is given. Same thing. After this point, you can see the reactant is becoming constant, product is becoming constant concentration. So as long as the concentration of the reactant product becomes constant, that means equilibrium has achieved. Third case. Third case, the only problem is this graph is given as product, while this graph is given as reactant. So that is wrong. Next one. You can see the reactant is decreasing, product is increasing, but linearly. So if it is linearly, it will never reach to an equilibrium. So the reactant will consume and become zero at some point. So therefore, if it is linear this way, that means it is not going to achieve equilibrium. Next, reaction rate versus time. If the rate of the reaction, see what is expected at equilibrium, that the rate of the reactants and the rate of the products both should become, rate of reactant and rate of product. Here also rate of reactant and rate of product. If both would become equal, right, then only we will say it is a equilibrium. So this is not equilibrium, this is not equilibrium, this is equilibrium. Okay, everybody, please look into the graphs. If you still have any doubt in the graph, you can ask me. Now, notice there is one important term called as equilibrium constant. So whenever an equilibrium is achieved, we will be able to generate a parameter which will remain constant. And that parameter is what we call it as equilibrium constant. To explain this, we will take the support of law of mass actions. Okay. What does that do? How does it help? Let's see. Okay. Law of mass actions. Now, according to law of mass actions, yeah, see, according to law of mass actions, we can say if any chemical reaction is given like this, A plus B is giving C plus D. Small a, small b, small d, and small c, small d are stoichiometric coefficients, and A, B, C, D are the chemicals. Then, according to law of mass actions, what it is been noticed? See, it is empirically observed. That means with respect to different experiments, once they reach equilibrium, we empirically take certain values, and based on those values, we try to figure out is there any formula existing or not. So what is the formula that has been identified is that rate of the reactants, right? The rate at which the reactants are converting can be always proportional to concentration of the reactant raised to the power of their coefficient multiplied by concentration of the other reactant raised to the power of their coefficient. Now this is a definition itself. The rate of reaction, how do we define it? Rate in the forward direction is equal to K forward, a rate constant. Kf is a rate constant in the forward direction. into capital A raised to power of A and capital B raised to power of A. So therefore, this is the rate in the forward direction, and kf is the rate constant in the forward direction. Okay. Now, same way I can write it for backward direction also. Rate of products can be written as rate of products, which is equal to k backwards into c raised to power of c into d raised to power of d. Now you all know that ABCD or stoichiometric coefficients. And if a reaction is happening, see, from reactant to product it is going, but in between there is no intermediate forming. Directly the reactant, whatever that is there, it is converting into product. And product directly are reacting with each other and forming reactant. So there is nothing in between. Such kind of reactions are called as elementary reactions, where the reactions are driven only by one step. So single step reactions are called elementary reactions. So imagine if reactant to product is an elementary reaction, product to reactant is also an elementary reaction, correct? So then in that case, we can say rate in the forward direction, if it becomes equal to rate in the backward direction, then we say equilibrium has been achieved. And you know that at equilibrium, k forward into this is equal to k backward into this. Got it? And now you know that k forward is a constant value, k backward is a constant value. Let me bring the constant values on the left hand side. So k forward by k backward is equal to c raised to power of c, d raised to power of d, a raised to power of a, and b raised to power of b. Now have you noticed that k forward by k backward is actually a constant value? This is a constant, this is a constant. So the ratio will also include a constant. So K equilibrium is equal to concentration of the products by concentration of the reactant. Okay. So I hope all of you understood how we get equilibrium constant. See, these concentrations are not at any time. These are only at equilibrium concentrations. So this is by, definition, these are all at equilibrium. So the concentration is always about equilibrium concentrations. Now, notice what are the types of equilibrium we generally observe. So, one is homogeneous equilibrium, the other one is heterogeneous equilibrium. Okay, and see, all reactant products and catalyst, if they are all in the same phase, then we call it as a homogeneous equilibrium. Best example you can notice here: nitrogen, hydrogen, ammonia. All of them are in gaseous state. Then we say it is homogeneous equilibrium. HCl, aqueous solution, NaOH, aqueous solution, if by chance it exists in equilibrium with another aqueous solution and water, this is also considered as homogeneous equilibrium. This is also homogeneous equilibrium. Got it? On the other hand, if the reactant product are in different phase, if you notice that reactant product or catalyst also, by the way, if the catalyst also is in different phase, then we say it is a heterogeneous equilibrium. For example, 3 moles of iron added to 4 moles of water to convert into Fe3O4 and 4H2. So you can see this is solid, gas, solid. So there are multiple states present. That means it is heterogeneous equilibrium. Alright. Now in heterogeneous equilibrium, we can add one more thing. N2, which is in a gaseous form, if you react with 3H2 gas, so that will give us 2 moles of ammonia gas. But here it looks like this is gas and gas, but this reaction is very well driven in the presence of iron solid. So solid mesh of iron, if at all it is taken as a surface on which nitrogen and hydrogen gases are meeting to form ammonia, then now there is a difference in the phase. Here it is a solid phase, the hydrogen and nitrogen are in gaseous phase. So if there is any phase difference, that means it is heterogeneous equilibrium. Got it? So everybody, please do check. Any doubt in type of equilibrium?
Sir,
No,
sir,
what is this? Yes, beta.
sir, won't the
Let me take this example again. N2 3H2 giving 2NH3. Okay. Because I have not given catalyst, what do we consider? It is homogeneous equilibrium. So if it is at equilibrium, as per the definition what we learned, that is product concentration raised to power of their coefficients by reactant concentration raised to power of their coefficients. So that will become K equilibrium. That is equilibrium constant. But since this equilibrium constant is represented in concentrations, we can write the same equilibrium constant as Kc. So Kc represents equilibrium concentration in terms of concentrations of reactants and products. Okay. So you can see ammonia at equilibrium, nitrogen at equilibrium, hydrogen at equilibrium, they don't, doesn't change as long as the equilibrium exists. And equilibrium constant in terms of concentration of the reactant and product is what we call it as Kc. Just like how we have Kc as one of the equilibrium constant, we can also have something called Kp. Now, how do we define Kp? This is in terms of partial pressures, of the reactants and products. Got it? Again, let me show you with the same example. Okay. This is something you can write in practice, everybody. See, N2 gas plus 3H2 gas, that is in equilibrium with 2NH3 gas at equilibrium, sorry, not this one, at T equilibrium. When time becomes equilibrium time, then let's say at that equilibrium, still there is some nitrogen left which has pressure Pn2. Similarly, pressure of H2 and pressure of NH3. These are called the partial pressures. If you know the partial pressures, so we can calculate Kp is equal to partial pressure of ammonia square by partial pressure of N2 plus partial pressure of H2 per cube. So this is representation in terms of equilibrium constant in terms of partial pressures. Okay. Now here is the important uh, assumption that all gases at equilibrium, obey ideal gas situation. Okay. All gases at equilibrium obey ideal gas. So that means volume of container in which the reactants and products are present here. So that volume, let us call it as V, and temperature of temperature of the equilibrium mixture, let us say it is maintained at temperature T. So then I can say partial pressure of N2 into V is equal to, number of moles of N2 into R into T. Okay. This way you can write it for partial pressure of nitrogen, partial pressure of hydrogen is equal to number of moles of H2 R into T. Similarly, partial pressure of uh, NH3 partial pressure of NH3 into V is equal to number of moles of NH3 RT. Got it? Now let me substitute this same partial pressures in terms of the number of moles. Again, so what do I get? Kp is equal to partial pressure of ammonia. Partial pressure of ammonia is number of moles of ammonia RT divided by V whole raised to power of 2. And next, partial pressure of N2. N2 will be equal to number of moles of N2, okay, RT divided by V and raised to power of 1 into number of moles of H2 RT raised to power of V whole raised to power of 3. Got it? Whole raised to power of 3. So now you can see number of moles of ammonia by volume. So moles by volume is nothing but concentration. So we can write this as concentration of ammonia R into T whole raised to power of 2 divided by N2 concentration into RT 1 into concentration of H2 into RT. For this, the whole concentration is, sorry, too many brackets. Yeah, RT raised to power of Q. So you can see this out that Kp is equal to Kc because ammonia concentration square by N2 into H2 cube. So that is equal to Kc. Okay. So Kc into RT raised to power of how much we have? 2 minus 1 minus 3. So that implies Kp is equal to Kc into RT raised to power of minus 2. Alright. So here we can write a general formula, right? So this is what we got it for ammonia plant. So Kp is equal to Kc RT raised to power of minus 2. Okay, so that's how we can calculate Kp. Now, if it is for a general equation like A plus B is giving C and D here, so at that in that case, Kp will be equal to partial pressure of C raised to power of C, partial pressure of D raised to power of D, and partial pressure of A raised to power of A and B raised to power of B, which is equal to Kc RT raised to power of C plus D, correct? C plus D, my that divided by sorry, Kc into RT raised to power of C plus D minus A plus B. So that can be written as Kc into RT raised to power of delta Ng. So delta Ng basically tells us how much is the difference in the gaseous moles of products minus reactant and products and reactants. Okay. So that is summation of number of moles of gases, on the product side here minus number of moles of gases on the reactant side. Clear? So this is the formula that has to be used here. So Kp is equal to Kc into RT raised to power of delta Ng. Right. So please do check how the formula is, right? And based on that, please complete this question, everybody. Look into it. If you have solved it or not, check out. Kp is equal to Kc into RT raised to power of delta Ng. Delta Ng in this case will be equal to 3 minus 2, which is 1. And Kc will be equal to Kp divided by RT raised to power of delta Ng. Kp value is given 1.8 into 10 raised to power of minus 2, that divided by RT. Okay. R is given as 0.0821 into temperature is 600 kelvins, right? So that into delta Ng, which is 1. Okay. So on multiplying this entire thing, approximately we are getting this as 3.65 into 10 raised to power of minus 4. You know, what are the units, by the way? See, you always check out delta Ng. Delta Ng is coming as 1 unit. So you know that Kc is representations of concentration. So the concentration will be molarity. Same way, see the second one. Calcium carbonate is giving calcium oxide and carbon dioxide. Okay. So in that case, delta Ng is how much? Delta Ng is 1 because this is solid and solid. We should only see delta Ng for gases. So therefore, Kp is equal to Kc, right? So this is raised to power of 1. So from here, Kc will be equal to Kp, which is 167 divided by 0.0821 into 1173, which is the temperature raised to power of 1. So this is coming out to be 1.734 molar. Please do check, everybody, if you got that. Right, Utsa, that's correct.
Sir,
Yes, beta.
what is the unit of measurement for constant?
What is the unit of
Measurement for that constant, Kc.
Kc? See, what is the power what you got here? Delta Ng is 1. So delta Ng is 1 means it will be having only molar concentration. Got it? So because it only depends upon concentration of carbon dioxide. So what are the units for carbon dioxide concentration? Say molar. This is the one. Okay. See, general form you can write it this way, that Kp is atm units multiplied to the power of C plus D plus minus A plus B. Done? Check. So Kp is equal to, how many gases are represented in atm units into delta Ng. Kc will be equal to molarity into delta Ng, and this is how you can relate. Clear? And notice that there are two types of Kp that we will always observe. One Kp is with dimensions, the other one is dimensionless. Okay. Here, when we use the Kp value, here we are using this Kp value with respect to the standard concentration or with respect to the standard pressure. So for A plus B giving C plus D, if at all I find out what is Kp value, Kp value is supposed to be Pc raised to power of C, Pd raised to power of D, Pa raised to power of A, and Pb raised to power of B, correct? But for that, you will get some dimensions. But in this case, when I write in terms of standard pressure or standard concentration, then they are divided by their pressures in their standard form. And in their standard form, P naught C, P naught D, P naught A, and P naught B all will have 1 bar. This is the standard form that is being taken, that for any gas, the standard pressure is always 1 bar. So now you can see there is no dimensions because the pressure terms are all getting cancelled. So Kp will be like that. Same logic with Kc also. So in the case of Kc also, you will have, everything in terms of 1 molar concentration. So if it is with respect to 1 molar concentration, this will get cancelled, this will get cancelled. So there will not be any dimensions. Okay. So remember two types of cases, or two types of KPs, one with dimensions and one without dimensions. Everything is clear? Ishman, you wanted to write this one, beta? Okay, I'll go to that page. First, please do check out KP and KC, then I'll go to the previous page.